I think there should be at least 10 more people joining. I hope they haven't forgotten. You all received my morning message, correct? Yes? And
Yes.
yes, wonderful. So then you know about the book that I posted in case you find some of the material here a little moving a bit too fast. All right, guys. So here is roughly where we left off. Perhaps I was able to cover slightly more, but let's be there for a moment. So would you remind, please, what it means for a function to be geometrically differentiable? Right? The idea of geometric differentiation means I have a curve. What do I do to that curve?
You zoom in and there is a line.
Exactly. You zoom in and you easily can remember it. Let me give you a hint, right? You are on Zoom, right? So you zoom in on it and you will see a straight line. Now, why is that representing the derivative? What do you think? Well, the derivative is the slope of the line that you will be seeing when you zoom in, correct? And you can imagine that without thinking about the fancy limits, what is the derivative? It's a tangent line, which means it's like a secant line that goes through 2 points that are very close together. Do you see that? So when you zoom in, you make this distance between the 2 points appear very large, and it looks to you like that line. And the slope between those 2 points is the derivative. Very easy, right, guys? Some people ask me sometimes, so what's the derivative is for, and why do we care about zooming in, and all sorts of questions. Those are very good questions, I presume. But of course, this is so simple, like effervescence almost, right? It's just a vocabulary word that you know it, and once you know it, you don't even question what you know it for, right? It's like when I say there is an Indian elephant and an African elephant. Well, it's some information, maybe useful, maybe not, but it's so easy for you to bother even questioning what's about. Good. So I hope you feel about this at least similarly. Now, here is a question I would like to ask you, guys. Remember, right? So we had this connection between differentiability and continuity. If a function is differentiable, then is the function continuous or not? Remind me, please. And as many as possible, guys, not 1, 2 people. I mean, I have 25 people here. I want to hear 25 answers, right? And not only yes or no. Would anybody actually, when you're responding, guys, tell me very briefly why? You cannot even make a very almost not even a sentence, not even a complete sentence. Why differentiability means continuity? Well, Sophia, very good. I would say similar, right? You zoom in, anywhere you zoom in, you see a particular line, right? So you think of a curve as a chain of very small line segments. And if you zoom in anywhere on the curve where it's differentiable, you are seeing a straight line, and a straight line is connected, correct? Straight line is connected, so that's a very particular instance of a connected graph. Well, so somebody says, Jeffrey says, continuity means straight line somewhere when you zoom in. Do you agree with Jeffrey? Because that's my next question, guys. Does continuity mean that you will see a straight line? No. That's a bit weird, right, guys? You think it means you see a straight line, some of you, but the answer is clearly no, right? If you zoom in on a curve and you see it's a straight line segment, it's continuous. So it's in particular differentiable, right? Even better than continuous, it's stronger. But continuity does not imply differentiability, right? Now, what does it mean for a continuous function not to be differentiable? Just try to imagine what it means in terms of zooming in. If you zoom in at a point where the function is not differentiable, what will you see or what will you not see? Understand? Continuous graph, you zoom in and you conclude no matter how much you zoom in, you think, no, it's not differentiable. What do you mean? you can see a sharp point, perhaps, right? Maybe you will not, because you cannot see a point. You always see everything, something around it, right? What you do not see is a line. Do you understand? What you do not see is a line. But the problem of that, that's just intuitively, guys. Yes, the problem is, of course, maybe you did not zoom in far enough. You understand? You cannot use a zoom in to be conclusively saying, well, definitely it's not a straight line. Maybe you have to zoom much, much farther and it will appear as a straight line. Yes, so you need to construct examples where you are absolutely certain, no matter how much you zoom in, you will never see a straight line. Good. Now, what are those examples? I believe I gave those examples to you before, but let's consider them again. This, guys, this wedge is not differentiable. Is that the right word to use, at the apex or at the tip? Apex is the tip, right? Yes. So it's not differentiable at the apex. Do you see why it's not differentiable at the apex, guys? Because if you make the apex or the vertex here the central point of your zoom in, you will see two broken lines. No matter how much you zoom in, you see that same picture. You zoom in, you will see that same triangle. Good. Now, how do I know that, guys? Let's try to see if I know that. Yes, I'll see a point between two lines, and that's very good. That's a good idea to visualize it, guys. Now, I'm going to give you right now a formula here, right? The formula for this wedge, or at least for this wedge that I drew here, its formula is 1 minus absolute value of x. That's my function. Now, with your permission, would you please tell me if I zoom in at this point? If I zoom in at this point, what will be my derivative? You understand? I'm asking what's the derivative at that point, and I'm asking you to tell me without carrying any significant calculations. Okay, wonderful. Alexandra, you see that? And what about the rest of you guys? What will I see when I say what's the derivative there? You see, guys, not one answer, not two answers. I want to see right now 30 answers.
Professor?
Yep.
1 second, let me turn.
What's up, Bullen? How are you?
Can you see me?
I see you.
All right. Unfortunately, I won't be able to keep the camera on as
No worries, Bullen. Nice to see your kids.
life is happening. So
yeah, I know.
The camera off now.
This is recorded, Bullen, and don't worry about it, right? I mean, if there is a kind of situation where I'm asking something big, guys. If you cannot turn the camera on, fine, don't worry about it, right? It's not, I'm just trying to maintain your awareness, that's it. Okay, Bullen, good luck with everything, okay?
I'm here listening.
Okay, good. Okay. Nicole, and you see the solution is 1, guys. Do you see why the solution is 1? Absolute value of x when x is negative. When x is negative, absolute value is it's going to make it a negative, right? So it's minus x, which means it's 1 plus x. And 1 plus x is the graph of a line. It's a graph of a line. Do you agree? And I can see the slope of that line, which is my derivative. I can see that slope right next to the x. It's here. Right? Now, what did I capture? Some of you, what is the slope here? The slope here is clearly 1. That's the slope next to the x. Good? Slope is next to the x. Good. So the slope that I will see here, it will be 1 times x. Exactly, Sophia. 1 times x means x. Good? And so I see without any calculations, because I know zoom in on a line, you always have the same slope. Good? I will show you guys in a moment that this type of thinking is, it makes it, I'm hoping, guys, that if you can follow my reasoning, 500 pages of calculus textbook will look to you like 1 page. Many exercises will look to you like 1 exercise, if you understand. Okay, this is not a difficult subject once you really understand what's about. What will be the slope if I zoom in anywhere on any point on the right wing? -1, precisely. Do you all see why it's -1, guys? Because absolute value will not have to do anything to the curve. And wonderful. What you see is this is the formula. 1 minus x is on the right, is the formula I see on the right. And the slope that I will see when I zoom in at any point here is -1. Notice that if the derivative is constant, that means all the slopes are the same, which means the microscopic line segments are aligned to form a macroscopic. Like microscopic forms macroscopic line. And that means it's just the slope of a line there. And it's always -1 here. I actually took the trouble to carry the calculation, not that it was necessary. So you can see 1 and -1 that we obtained here, right? This is from the left, this is from the right. But you never needed to do any calculations. You right away could see the slopes are this, right? And so if I zoom in, you can now see what happens. If I actually want to calculate the slope at 0, that means what? That means I select the apex point. I select the apex point, which is the point 0 and 1, and I select any point near it. You see? This is now the line segment over which I calculate the slope, and that slope will be 1. Yes? That slope is 1. If I do that, on the other hand, if I select any point in here, the slope over that edge will be -1. So you understand? So what happens is at 0, the function is left differentiable and it is right differentiable. You understand what I mean by left differentiable, right differentiable? In other words, if you only look from the right, it looks like a line. If you make this point the left edge of your screen, it looks like a line. If you make this point the right edge of your screen, it looks like a line. So it's right and left differentiable. But it's not differentiable because the limits do not agree. Very simple, correct? Guys, you're all with me, right? All what we did is I'm hoping you see beyond the symbols, beyond fancy words, and you see all we're talking about is line. And all we're talking about is slopes of line. So something very, very lowly. Okay. Now let's move on. Guys, so this is somewhat not differentiable, but do you understand that I can also create non-differentiability at infinitely many points by creating this zigzag pattern, right? Which I don't know, zigzag sounds good enough, but in German, this type of thing, those teeth, it's called zackig, which I somehow is exactly how I think of what it is. And guys, this picture here, you see this picture? Now, this picture is trying to illustrate something that is even worse, even less differentiable than in the picture of that wedge. Do you see why it's worse? It's worse, guys, because you are thinking if something is, another nice word for differentiability is you say something is differentiable if it is smooth, if you can touch it and not be cut. All right, over here you can actually be cut. You can see a blade there, right? It's a broken line. Now, this broken line, this wedge has an angle. Do you see that, that this wedge, here it is, there is a fixed angle. But over here, the sharpness is infinite because it's like this. You see the angle, as you move closer to that zoom, you're seeing a sort of triangle that has a smaller angle. Another thing that you can also see by the graph is, look at it. If you fix the apex as one of your points and fix a point from the left, like over here, you can see that as you slide the left point closer, the slope becomes more and more steep. It becomes infinity. It becomes infinitely steep as you go there. And on the other direction, if you select another point to the right, now you slide the point to the right closer to A, it now becomes negative slope. So it gets to minus infinity. So here, the left hand is plus infinity, right hand minus infinity. So neither left nor right limit exist. Okay, so that's a much worse type of non-differentiability because it's neither left or right differentiable. It's very sharp. Good? Amazing. Now I asked, I think you remember that story, right? I asked you this. Now notice that on the graphs that I produced, like this graph. Right here is a point of non-differentiability, but if I move ever so slightly to the right, I have differentiability. If I move ever so slightly to the left, I have differentiability. Is it possible to have a function that's differentiable nowhere and yet continuous at every single point? And I answered that question last time, I believe, right? But do you remember? So all you have to do, guys, to see a non-differentiable function is go to the New York Aquarium, right? Do you know that song, and the shark deer has big teeth? I'm not sure how it goes in English. Do you know it? Mac the Knife song, no? Und Makif, der hat ein Messer und man sieht das Messer nicht. Do you know the song? No? I should play it to you. It's a good song. It says basically, and the shark has big sharp teeth, but you see it in his face. And Mac the Knife, he has a blade, but you just can't see that blade. So sharks are entirely made of blades. Their skin is covered by, not by scales, but by teeth. They're called dermal denticles. If you look at the shark scale, it's a miniature copy of their teeth. And if you look on their teeth, you see more teeth on top of teeth, so to speak, right? So a shark gives you an inspiration of how to construct that function. I showed you, I think, a graph of that earlier. Now, this is roughly the shape of a shark tooth, and on top of it, I exaggerated their size. You will see more teeth. And if you zoom on top of them, you will see more teeth. And the function, you don't have to worry about. It's defined out of an infinite series. You have to, of course, prove that it has those properties, and it looks like wedges upon wedges upon wedges. I mean, that's one example of such function. There are many, okay? Wedges upon wedges upon wedges. So I drew it kind of poorly, but just Google nowhere differentiable function, and you'll see a nice picture for it. Good? Of the idea, at least. Now, very, very quick comprehension check, guys. Without doing any computations, tell me what's the derivative of this function at x equal to -7, please. Exactly. So I hope, guys, as you're typing in 5, you're not, if those that haven't written anything, it's not because you don't understand, it's just like it's too trivial for you to type, right? It is a line. You zoom in on the line, you see the same line, and all you have to do when you ask for the derivative is you're measuring its slope. Yes? Now, you're not confused at all. The idea of the derivative is very solid in your mind, correct, guys? Now, let me slightly confuse you guys, right? So if you go to more advanced mathematics into Calc 3 and beyond, if you go into differential geometry, the derivative is no longer defined to be the slope, it's defined to be the tangent line, okay? Now let me try to explain to you why you depart from slope and go into the tangent line itself. If you're obsessed about the geometric perspective, guys, if you're obsessed about the geometric perspective, let's try to look at this black line. Do you see this line? This black line. Now, this line is suspended somewhere in space, and objectively we have a line. But what's not objective is what we mean to be the slope. You understand? Slope is really reporting our perspective, how we are looking at it. Do you agree? Look at it. Is this horizontal? Well, it is horizontal if it's horizontal relative to the way I look at it, relative to my eyes. But if I decide to lie my head on the side, it's now vertical. Do you agree? You might not believe that's true because you feel the force of gravity, right? So you think that there is some sort of actual horizontal. But if you turn off the force of gravity, you will lose the sense of actual horizontal and actual vertical. And those things are just subjective reports of your perspective on that line. There is one line, and you can look at it in such a way that it appears to you vertical or horizontal or at any other incline. So slope is not intrinsic to a line. You understand? And when you study geometry, you try to communicate what's intrinsic to a particular geometric shape. And I will show you that this type of thinking, hopefully, it is a type of thinking that will allow you to very quickly figure out many solutions or unify some ideas together. Okay, so for instance, guys, this line, if I say that the x-axis and the y-axis are in agreement, the y-axis is perpendicular to the direction of gravity. If I say so, then this line supposedly has the equation y equals 1 times x plus 0. But I could draw a line parallel and a perpendicular one. Why? I could draw it in the green coordinate system. In the green coordinate system, since the black line is parallel, its slope is 0. Do you understand? You see what I'm saying, guys? You're not confused, I hope, at all, right? Relative to the green xy axis, the slope is 0. Relative to the black xy axis, the slope is 1. It should not be very difficult to you guys. You probably understand moral relativism. So this is just an objective relativism, much better than a moral one. Good? Yes. You understand what I mean, guys? I don't believe in moral relativism, but I do believe in relativistic perspective. Okay, guys. And here, let's try to apply it. Guys, don't worry if you don't get it right away, but try, okay? We will talk about this idea later. If you get it, then it's not even for the idea itself, you see? I mean, you might think, oh, I can calculate this question one way or another way. The perspective matters as it makes you smarter, hopefully, if you actually adopt a perspective that is, that gives you deeper insights. Okay, so here is what I am trying to ask, guys. Okay, and I might actually draw another curve so that I will confuse you a little bit less. Okay, I mean, and actually, by the way, remind me, you should all stay. There is something that will be confusing here, is in a game of what, when, where that we will play after this class. Good. See if you would be able to answer that question. Okay, guys, so here we go. Okay, guys, my question is, you know what is the derivative of x squared? I'll just write it like this. What's the derivative of x squared? We calculated it many times by definition. What's that derivative? Could you tell me, please? It is 2x. Very good. We calculated it many times. Remember, we did the limit stuff, right? We will do it again in a moment, okay? In case you forgot. So we know that this derivative is 2x, okay? And then we have the derivative of root of x, okay? Which, I mean, if you avoid some problems, let's say there is limit laws. We treat it as if it's obvious that the limit of a root is the root of the limit. We did not prove it. We actually, by the way, didn't prove any of the limit laws, but if you studied delta epsilon, if you looked at those notes, I'm sure all of you did, then you would understand that those limit laws are not laws given to you by the governor. Those are the laws given to you by reason. Good. So here is my question. What is the relationship between this derivative and that derivative? Okay. What's the relationship? Okay, guys, and let me draw the inverse. Inverse of x squared and root of x, yes, but what's the relationship of the derivatives? Okay, so suppose that what I want to do, I know the derivative of x squared is 2x. How, without doing anything else, do I know the derivative of root of x? Let's try to look at it from the geometric perspective. Okay, guys, here is the y-axis, here is the x-axis. Okay, so Sophia, you are almost there. Okay, it's good. Slight modification to what you say there. Okay, so we have root of, this is the curve y equal to root of x. Okay, guys. And if you just want, we can write coordinates to it. The coordinates are x and root x. Okay. Now, this is my curve. And imagine that what I want to do, I have this astronaut walking on this curve. If he's walking on the x-axis, here is the point A, right? And then the corresponding point here is root A. You agree? So he wants to know the slope of the tangent line. He wants to know the slope of the tangent line, which is simply in Leibniz notation dy dx, right? So a short displacement in x, short displacement in y, that's just notation. Good. We want to know dy dx. Okay. So for this green astronaut, the x-axis is horizontal and the y-axis is vertical. So far, all is clear. Now, let's place an astronaut on the y-axis. This astronaut, okay? And he looks up on the same line. Do you agree? They're all looking at the same tangent line. First of all, in terms of the function, what function does he see? So this guy is saying, the green guy says that he is seeing y equal root x. What would the blue guy report as seeing? The blue guy says that he is seeing what? Well, use the right labeling. Okay. What is the other guy seeing? He is seeing, well, Erin, you don't mix your symbols. He is saying x equal to y squared. Now, here is a difference between what most of you do and what I do, okay? First of all, guys, what does the equation y equal root of x mean? Okay, for the green person, let me just not use those y and x and just speak about the green person. The green person observes that every position on his horizontal corresponds to a vertical position that is the root of the horizontal. You understand? He's seeing that the vertical is the root of the horizontal. Are you with me? The vertical is the root of the horizontal. Notice my explanation does not say x or y. Now, the blue guy, what will he be seeing? His horizontal is different from the horizontal of the green guy. Do you agree? Yes? So if he speaks about his horizontal and his vertical, what is he seeing? He's seeing that he's saying my vertical is the square of my horizontal. Do you understand what I mean, guys? What it is when people say mathematics is a language? Look at it. I have this pen, right? This pen is moving away from me and becomes smaller. But what you are saying is this pen is moving towards me and becomes larger, right? It's just a difference in perspective, which is pretty interesting that people of New York don't have that ability. Yes? Difference of perspective. So what we have here is he's saying basically, look at it. You can just see it from the equation. You just take the square on both sides and you see that the same equations are what? It's the same as y squared equal to x, right? Y squared equal to x, and this guy is saying, okay, if I'm standing on the horizontal, the blue guy, my horizontal position corresponds to a vertical position of square of the horizontal. Good. Now, tell me, please, what slope does he measure when you look at this line? When the blue guy looks at that line, what slope does he measure, please? Do you see that he's dealing with a square function? You agree? The root function and the square function are the same graph, just viewed from different perspective. That's what I'm trying to say. Now, the blue guy, what slope does he measure? Simple question. Oh, guys, what slope does he measure? You know that. Look what is his position. What's the slope? No, Brian. All right, you just said here. Look at it. Oh, you see, you are bothered by the symbols. Derivative of x squared is 2x. What does it mean, guys? It means if I have the vertical coordinate is the square of the horizontal coordinate, the derivative, if I'm staying at a horizontal coordinate, is twice the horizontal coordinate. Do you understand? Look at it. The way I speak, I don't mention x's or y's because those are just symbols to assist communication rather than to indicate meaning, right? Very good, Sophia. You're getting there, very close, right? Except you're mentioning x. Don't stick to the x. Look at it. He needs to measure the slope at what point? At what horizontal point? At this horizontal point, yes? And what's the derivative of a quadratic? Do you understand what is when you say a derivative of a quadratic? When I say derivative of x squared is 2x, guys, there is no such thing as x. What I'm saying again, if I look at a parabola, at a quadratic, the result is that that the derivative at a horizontal position, the slope at a horizontal position is twice the horizontal coordinate. Do you understand? When I look at a quadratic, I look at the horizontal coordinate and I multiply it by 2. So what is the horizontal coordinate for the blue guy? For him, this is the horizontal coordinate, yes? Yes, so it's so it is, but you, Alexandra, you are reporting it for the green guy, right? For the blue guy, the slope is this. Look at it. That's why Olabny's notation is so nice. For the blue guy, the slope is dx dy equal at this point to twice root a. Do you understand? Because my horizontal, you see, if I'm a blue guy, y-axis is my horizontal. Are you with me? Right? And the reason it actually bothers you, maybe in fact I will not wait, since some of you don't want to stay after class, maybe we will play that game in a minute after I finish explaining this, because it's so related to this. You see, your conflict is this, guys, right? This looks to you like vertical and I'm saying it's horizontal, right? So you're confused. You think, oh my God, what is he bothering us for? But no, you are the blue guy. For the blue guy, the horizontal is the y-axis. And so he understands calculus very well, and he understands, aha, right? The slope is just twice the horizontal coordinate because he sees a parabola. You understand? He sees x equal to y squared. What is x equal to y squared means my vertical is the square of my horizontal. Do you understand? Forget about x squared equal to y, doesn't matter, right? My vertical is the square of my horizontal. That's a parabola. And all I need to do to find its slope is multiply the horizontal coordinate by 2. Yes? If you understand, do you understand me, guys? Are you with me? So the answer is that dx dy is 2. Now he reports that, he reports it to the green guy. He says, I measured slope 2 times root of a. Tell me what slope is the green guy now going to measure? Now that he knows that the slope that the blue guy measured, what slope does he think this function has, the green guy? So now the green guy says, aha, what's my slope? What's my slope at this point? Exactly. My slope at this point is what? Now we can go back to the red coordinates. It's dy dx, which is what, guys? Dy dx is the same as 1 over dx dy. Do you agree? Just take a reciprocal of it, which means 1 over 2 root a. That's the relationship. It's such a simple, trivial relationship. You agree with me? You see, if you're confusing, my God, it's so confusing. I can calculate root of x so easily. Well, you can calculate, but it's a meaningless thing that you calculate, guys, right? First of all, and you see, you just what I'm showing you guys. If you think this way, you can connect a lot of functions. They look to you like the same function. So for me, root of x looks very much like x squared. They have very many similar problems. I right away know that root is continuous. You understand? I mean, I can justify the limit laws geometrically this way. Good. So you understand why are you not fast with it? Because you confuse vertical and horizontal and all that stuff, right? So then what we do right now, guys, we take 2-minute pause from this recording and we are going to do a question from what, when, where relating to this, and see if you can answer it. Yesterday, we played very well. Here it is.
Интересно, а философия осталась? Или почему бы в Америке?
Ну, мы смотрим по нашему времени. У вас не принялся вопрос.
Ну давай. Внимание, тест
Attention, Stroop's test.
Струпа. Господин Низамов, послушайте меня внимательно.
Mr. Nizamov, listen to me carefully.
Да, с вами сейчас будем играть.
We will play with you.
Назовите последовательно и быстро цвета на этой карточке.
Name quickly, that's not the question, name quickly and fast the colors on this card.
Прошу.
Красный.
You see this, guys? You don't have to worry. You see, it's red, green, you know this type of thing, right? So you have one word written and it's in a different color. I'm sure that you've taken psychology or have known about this thing, right? It is exactly what we were having problems with. Not color tricks, not at all. You will listen to what this experiment is supposed to indicate. That's exactly the kind of thing that was causing you trouble in understanding what this weird person was talking about a moment ago, right? Me, I mean, if you don't understand what I
Красный, желтый, черный, зеленый, оранжевый, голубой.
Каждый раз вы, почти каждый раз
Almost every time you stopped and thought.
задумывались.
Да.
Этот тест
This test
в 1935 году придумал психолог Джон Струп.
This test in 1935 was invented by the psychologist John Stroop.
Для диагностики способности выделять определенные признаки и игнорировать другие.
For the diagnosis of the ability to emphasize certain features while ignoring others. Like vertical, or this is horizontal now I'm saying, right? To be able to do that. Same thing.
Внимание, вопрос.
Attention to the question.
А с какой целью в середине 20 века в Америке некоторым людям предлагали пройти вот такой тест Струпа?
Let's see if I can find a better video.
Тест Струпа.
По-русски написано.
Okay, guys. Now the question is, for what purpose in the middle of the 20th century certain people were required to pass this test of Stroop? And if you don't understand, this is written in Russian. It's the same thing as before with the English words, but this one is written in Russian. What was the purpose in the middle of the 20th century to force people to take this strip? Well, exactly. Well, somebody immediately understands. To figure out, well, it's too bad you answered so fast, but yes, to figure out whether or not you're a Russian spy, because if you can read it, you understand the meaning, you will be slowed down, right? And yes, but at least you enjoyed it. And let me just show you the ending.
Желтый
And you see, you
человек
have a
легче
similar
называть
thing
китайского языка.
for
Просто на-
Chinese.
Тут
It
все
is-
понятно. Красный, желтый, черный.
If you don't know Chinese, you will read it very fast. But if you know Chinese, you will not read it fast. Good? Wonderful. Let's get back to the lecture. There will be more questions, but congratulations, Alexandra. Right. I also noticed it immediately. Actually, my brother did. Let me not take the credit, right? My brother just noticed right away. I noticed some other things. So good. Understood? And now if you understood, guys, if you understood, you will now not have any problem telling me what's the graph of the derivative. Do you understand what I'm asking? This is a curve. I am interested in plotting the derivative of that curve. You follow? You understand what it means to plot the derivative of that curve? It means that anywhere I look, let's say I look at this point, for this point x, I want to know what's the slope. The y coordinate will be the slope at that point. Okay, so if you cannot draw it, you can communicate it very easily. You can tell me what to write over this interval, what to write over the next interval, because obviously, well, so quickly tell me what is going to be the graph here. You can even tell me if it's if specific values, their sequence. You can say this, this, then this. You have 2 minutes at most. If you stay after class, I have very, very interesting questions for you guys from where I gathered, right? Well, exactly. Well, okay, one person has answered it. Okay, it looks like Moshe took a copy of it and pasted it, but maybe not. Good anyhow. Don't need to do extra work. It's always smart. The joke today. I am joking, Moshe. I just looked exactly the same. Spaces are the same. Right? I imagine that when one person answers, the rest of you just look at it and just copy it, and then I can think, oh, everybody understands. Yes. Well, Elazar, slightly off, no? All right, guys, let's do it together. Let's say we do it together. Here what we do, guys, look at it. You zoom in at this segment of this curve, right? What are you seeing? You're seeing a line. Therefore, the slopes at any point you zoom in along that line segment are going to be the same slopes, yes? So I will report a horizontal line. Now, what is that horizontal line I report? It suffices to take this point and that point to measure the slope, 3, 3, and 0, 0. Do you agree? So that slope is from this point, which is 3, 3, and this point, which is 0, 0. So the slope is 3 minus 0 divided by 3 minus 0, or 1. Good? So I just did it long-winded thing, hoping that you understand it, guys. So that means that here, the slope is 1. Yes? Here the slope is 1. Do you understand why it's a constant? The derivative graph is constant because at this point of x, the slope is 1. At this point of x, the slope is 1. So you end up reporting a constant slope. Now, between 3 and 6, the slope is 0 because it's a horizontal line. And you report a horizontal line segment. Later on, what about this part, guys? This part, the slope is minus 1. Do you all see why it's minus 1? You move 3 units to the right and descend 3 units down. So that's minus 3 over 3. The slope is minus 1. You don't pay attention to the graph, whether it's above or below the x-axis, only to the slope of the line segments that are making it up. And the slope after 9 is 0, which is what I drew over here. At those points where you have discontinuity of the derivative, that's where the derivative fails to be existing. Good? Everybody clear, guys? Anything I need to add to this thing? It's easy, right? This is a curve that is actually built up of a few line segments. So all I need to do is figure out the slopes of those line segments and plot those slopes over the intervals for which those line segments are stretched. Yes? All right, so the next thing is going to cause me a lot of headache, but I hope you all understand it. Now, what are you going to do? If you are given a curve that does not look like a straight line, what do? Obviously, I already hinted what you do, guys. You can imagine it's built of many microscopic line segments, and you can measure the slopes for those microscopic segments and plot those points and connect them. Yes? So that's what you can do. So let me just maybe draw something new, just in case. Here it is, guys. Look at it. Suppose that this is my picture. Look at it. Okay. So if this is my picture, I can imagine breaking the interval into small segments. Let's do it in orange. Okay. So here is a segment, here is a segment, here is a segment. I can imagine the segments to be of equal width, just very close to one another. Okay. And over, let's say, a particular segment over here, I have a line segment, you see? Now, and here is the corresponding line segment. Here is the corresponding line segment. So this looks like a positive slope. I cannot, if I don't have any numbers, I cannot be sure about what slope it is, but I know it's positive, yes? So I draw above the x-axis. Basically, it is a line because over this segment, it's just a line. The slope is the same, right? Now over some other segments, so for example, maybe over this segment, here it is. Here is the width. Now the slope here is negative, so it would be, let's say, so that's what I mean. This is the graph, right? The slope here is negative, so over this segment, it's somewhere here. And so what you would have is a lot of edges like this. A lot of segments that are becoming like points. And if this mesh, if the partition is very small, those line segments will look like points and it will generate the graph. Good? You might as well, instead of doing those points, you might as well take the midpoint, and that would be a point that you have on this derivative graph that you can connect by a curve. You understand what I said, guys? I mean, in fact, I don't think I needed to explain it, right? What is the derivative? It's just a segment, a small segment, a small linear segment in a chain of line segments, right? We think of curves as being built of many microscopic line segments. Good? So what is that situation here? Here are the line segments that I approximated the curve by, and this is how I plotted the derivative, roughly speaking. You can see that here, the curve is positive, so here is the derivative, here is positive. Then over here it gets to be less and less positive. That's why the green curve decreases. Understand? I don't consider if the graph of the black curve is above or below the x-axis. I am only considering whether the orientation is this way or that way of the line segment. So here the orientation is moving up, so we have positive slope. We are moving up, the line segments get more and more horizontal. Somewhere here they get horizontal, the derivative hits 0. Afterwards, the derivative becomes negative and returning to 0 somewhere here. So that's where it's returning to 0, you see? Then it begins to climb until it reaches this point where it's 0 again. So here it climbs, reaches the maximum somewhere over here, and then decreases back to 0. So this is all slopes, right? This means now it's horizontal. Afterwards, it becomes, after this point, it becomes negative, and so, right? So this is roughly the shape of this curve, which is not precise because I don't know the precise value of the derivative. I can make it more precise by carrying measurements. Good? Understood, yes, guys? Any questions on that, guys? So such questions were on some of my exams. You can look afterwards in the review and see if you can plot it. The idea of those questions is naturally to try to teach you what is the derivative and how it fits in the construction scheme of curves, which if you understand, it should not be a problem at all. Clear? So when people ask me what to do here, I mean, it's already kind of a question that it means that you're not comfortable with the ideas. They're not natural to you, right? What I hope to teach you is you look at something that you never saw before and you figure out what to do. Not, that's what you do in physics all the time. Okay, it could be very major and that's a great discovery, or it could be very minor, or minor enough not to be published. There are many formulas that nobody will be writing in books. You have to kind of come up with those formulas all the time when you are using the subject for applications. Good. Now let's move on to the next lecture, guys. Oh, polynomials. Oh, it's so nice that that we're back to them. Without me opening that lecture note, remind me, please, what is a polynomial? And try to give me an intuitive explanation, right? I mean, not just a definition that makes no meaning to you. Intuitively, what is a polynomial? Okay. Okay, so 2 people answered. Good. What about the rest of you guys? It should be immediate. Immediate. Addition and multiplication. You understand, guys, right? That's the idea. Only addition and multiplication are allowed as procedures. Wonderful. Good. So they are the simplest functions we have. That's why we are interested in polynomials. Now, here is an example. Look at it. You see, what is x, guys? Anybody will tell me what is x? You understand my question, guys? I say f of x equal to, what is x? Is there a guy named x? Exactly, an input. You understand, guys? X means give me the raw material, which in this case is a number, and I will tell you what to do with the number, right? So here it means take 1 minus the number plus 2 squared plus the number plus 2 minus 1 cubed plus 5 times the number minus the number squared. Notice I never use the word x, okay? And the reason I try to show you not to use the word x, because you see, guys, some meanings are opaque to you because you are too familiar in writing them one particular way. So for example, y equals x squared. Well, you think, okay, y equals x squared, you think parabola, but there is no y, there is no x. There is, it just what this equation is saying when you're plotting it, you're saying plot the graph where the vertical coordinate is always the square of the horizontal coordinate. You understand? And if you say it this way, you understood the meaning a bit better than if you say y equals x squared. Clear? You just have to translate and see the meaning and see what is it that you are looking at. It's just like when you read multiplication, you don't say M-U-L-T-I-P-L, you know, right? You don't focus on the letters, you're focusing on the full meaning. So you look at it, what I can do, guys. I can neatly rearrange I can neatly rearrange the operations to group them by not using x at all, using x once, using x twice, using x 3 times or more, right? So that's what happens over here, guys. So you can do the algebra, it's up to you. But look, you see what happened here, guys? Once I simplified it, I say we have -2 plus 4 times x plus x squared plus x cubed. I decided to group by increasing involvement of x. I could have grouped in the other direction, but you will see later that sometimes doing it one way is preferable, okay? So in your previous classes, you probably started with the biggest term first and then went to smaller terms. But in some subjects, it's much nicer to present it in this way. So it doesn't matter, of course, right? So you see what happened here. So this is x multiplied once, twice, 3 times. And that's the full polynomial form. That's why you define a polynomial to be this structure. And maybe why do they speak in school differently? Why do they say this is a polynomial and not explain this? Because I presume they get tired explaining it to people, right? I mean, here they memorize it, they pass the exam, they live on. Which, as you get older and less naive, you kind of do. This is the definition of a polynomial. Yes? That's supposed to express that we used x up to n times. Now let's begin trying to come up with shortcuts. Remember, guys, we did by definition, but the definition will allow us to produce shortcuts, so we don't have to do complicated calculations every time. So let's begin to try to come up with that definition. What is the derivative of f of x equal to c, please? What's the derivative without any calculations? Because it's constant, but be more specific, Christian. Because it is a horizontal line, right? Constant, you have to always think, guys, it's a horizontal line. So what slope do I measure anywhere? I measure the slope 0. Good? Wonderful. So the slope is everywhere 0. And you can write it as d dx of c is 0. Now, another very similar question, guys. If f of x is equal to x, what's the derivative? Oh, Sophia, you already moved to Calc 3, right? That's the derivative in Calc 3 sense. Derivative for us is the slope. Remember, I hope you're not confused, guys, right? I'm just preparing you, right? There will be a juncture once you're taking Calc 3 in just maybe a semester or two. Then you will see that the derivative, if it's not this way, the derivative is now the tangent line rather than the slope. But for us, it's still the slope of the tangent line. You understood why we switch perspective, guys? Slope is subjective. It depends on your point of view. The line is not subjective. There is a tangent line, no matter how you look at it. Good? You see what subjective means, guys? Subjective means from your point of view. Yes, he understands. Do you hear the screams? You do, right? So Sophia, okay, so guys, what's the derivative of f of x? I'm ranting. What is the derivative of f of x? Come on, remind me now, quickly. One. The derivative is 1. Why? F of x equal to x is a line of slope 1. Yes, so for us, we report that derivative is 1. But if you are taking Calc 3, you can report the derivative is x. Good? No confusion, correct, guys? You're all with me. Now, this is the limit by definition. Now, suppose we have f of x equal to x squared. F of x equal to x squared. What's the derivative? We already know that, right? We can do that. Now it's a bit hard to see what it is when you just zoom in, so you do the calculation. Here is the calculation, and you get 2x. You agree with me? We did the calculation like at 10 times already, probably more over the class. Now, help me please. Now, here is a challenge. Now, f of x is equal to x cubed. What's the derivative? You can try to guess, of course, but I want you to prove that your guess is correct. You understand? Some of you took calculus before or not, right? Or know or can guess well. But is your guess correct, and how do you prove it? That's good. Okay, so we have 2 people guessed. Okay, Alexandra had a guess, Kevin had a guess, but of course, how do you prove whether or not your guess is correct? Okay, let's do it together, I suppose, guys, right? But you should be able, you see, I mean, really a good student, I give that as assignment. You never taught us how to do this. You should figure out. Right? You should be able to figure such things out. Now, here is what you do, guys. Look at it. All I have to calculate is the limit as z goes to x of z cubed minus x cubed divided by z minus x. Yes? Divided by z minus x. Now, I need to get rid of z minus x in the denominator. How do I factor a difference of cubes? I know how to factor a difference of squares. How do I do with the difference of cubes? If you cannot figure it out, to your rescue comes long division. Long division, guys. You remember how to use that long division? We can practice it if you don't remember. I can try to, again, in explaining, I mean, I can show you how to do the procedure, or I can try to explain why it works. So here is z cubed minus x cubed, and this is z minus x that I divide by. So I need to multiply this z by z squared to get z cubed. So that's what I do here. And so what I subtract is z cubed minus x z squared. You understand? I just take this. This is what I need to multiply by this to get z cubed. And then I multiply it and subtract what I created. You see this? It's just this expression multiplied by z squared. When I subtract, what happens? The z cubes disappear. Minus x z squared becomes x z squared minus x cubed. Now, what do I need to multiply z minus x by to get x z squared? I need to multiply by x z. Are you with me? So I put plus xz, I multiplied by xz. I have this line, subtract. What do you have? You have x squared z minus x cubed. Now what do I need to multiply to this z minus x to get x squared z? I need to multiply by x squared. Here's that x squared. I multiply, subtract, I get 0. This is my factor. So that means that z cubed minus x cubed is z minus x times z squared plus xz plus x squared. Now, there is something very poetic about differences of n powers. And I forgot to show it to you, but it reminds me of Oscar Wilde, of the Nightingale and the Rose, which I will send you a voice recording of, since I'm not sure if you would read it. So, what is that situation, guys? Like you see, I spend a lot of trouble, stopping, explaining things. So look what happens here, guys. And you will see maybe later on what does it have to do with Nightingale and the Rose. That may be an assignment, extra credit. Good. So look what happens here, guys. Look what it is. So z cubed minus x cubed. It's z minus x times, I begin with z squared. Z squared gives one of its powers to x, and now I have xz. You see? The sum of the powers of z is, and z and x is 2, one less, okay? Next, z has one more power to give to x, so it would be plus x squared. Z is gone. Z has withered and died away. No z. Do you follow? Do you understand what this process is, guys? So I will show you in another example. afterwards, okay? So then look at it. Once I cross it out, I take limit as z goes to x of z squared plus xz plus x squared, and look what happens. Z becomes x, so that is x squared, right? The sum of the powers of z plus the sum of the powers of x is 2. So that's x squared, so that's 3x squared. So the derivative of x cubed is 3x squared. Now, what your next goal is to tell me what's the derivative of x to the 4. You can try to guess it, and then try to figure out how I factor a difference of degree 4 powers. Okay, Sophia, good. Okay, good. Okay, well, I mean, I suppose good. I mean, this is not too hard to guess. Here is my question, guys. How do you factor a difference of degree 4 powers, right? So when you take the derivative of x to the 4, what do? You take limit as z goes to x of z to the 4 minus x to the 4 divided by z minus x. You agree? Yeah? So how do I factor z to the 4 minus x to the 4? Let me give you a hint. So z to the 4 minus x to the 4. You can verify that's to be true in a moment, right? So that is what? That is z minus x multiplied by what? What's the next power? What do I write here? So I write here z to the power of 3. I begin with 1 power less. No, Duada, it's not z plus x. Z minus x times z plus x will be z squared minus x squared. This is z to the 4 minus x to the 4. No, it's not like that, guys. Again, you didn't look at the long division or notice the powers. And that's actually why it will be so relevant for you to listen to the nightingale and the rose. The nightingale gives its strength to the rose. X is that rose. Z cubed plus. Now, one of the powers of z was given away, so that is x z squared. What's the next stage? Plus. Do you see what's happening? Z had power 3, now it gave 1 power to x. What's the next stage? X squared z. Very good. Next stage is x squared z. And what's the next stage? X cubed. There is no more z. Just like in that story. You understand? Now it's not arbitrary, guys. You understand how you do that? If you forget that formula, you first apply long division. If you do not know long division, learn long division. Right? It's terrible not to know that for this class. Right? Okay, so that's z, and we divide that by z minus x. This goes out, and now I can push the limit. Look at it. When I push the limit of z becoming x, what do I get? I get x cubed plus x cubed plus x cubed plus x cubed. How many copies? 4 copies. Do you see that? 4 copies. You all understand why it's x cubed, guys, right? Because z becomes x, x stays the same. Now, what do we get here? We get here 4x cubed, as you predicted, guys. Yes? Wonderful. You understand that you should expect for your exam that I will make you do things by definition, right? You might know shortcuts, but I don't care about that, right? I mean, I don't care what you memorized. You will show me that you understand how to carry it by definition. Okay, it's 4x cubed. Now let's go back to that lecture notes. Here it is, guys. By long division, if you don't remember it, you see this is what you do if you don't remember it until you notice the pattern. And the pattern is very simple. You begin with z minus x, and then z is to a power 1 less than before, and it will give its powers 1 by 1 until there is no more z. Okay, guys. Now, if you understood it, you will tell me how I do that by definition for x to the power of 5. So x to the power of 5, when I take the derivative, that would be a limit as z goes to x of z to the 5 minus x to the 5 divided by z minus x. Tell me, how do I factor the numerator? I mean, you can guess, guys. Today you guess correctly. Tomorrow I will confuse you and you will guess incorrectly. And I will do that. So how do you verify that you are right? So this is limit as z goes to x. How do you factor the numerator? Please help me. What do I write for the numerator? How do I factor a difference of 5 powers? No, I begin again, guys, and you can do it by long division. It's just, so it's z minus x. What do I write next? Next what? The full thing, or if you cannot do the full thing, what's the next term? Z to the 4. Next. Or if you can write the full expression, what do I write afterwards? Not z cubed, no. Okay, some people see the pattern, good. Next, look at it, z, you're not listening to what I'm saying. Z begins to give its energy to x. So what do we get? We get here plus x z cubed, right? Z is depleted, z gets tired. Z runs out of life force, explaining every single thing or feeding 1 power at a time. So the next thing is what? Next is what? X squared z. Do you see what happens? Z squared. The powers of x and z add up to, they add up to 4. Okay, and then what next? You see what happens now? Now it's x cubed z plus x to the power of 4. Do you see what happens? Z had all the power, 1 less, 1 less, 1 less, no powers left. That's how you factor difference of nth powers. And we will verify that that's the way we do that for an arbitrary n. But how do you remember this? Imagine like it's say tomorrow you don't remember it. What do? You do long division. And then you recall the pattern. You must always have a way to find your the thing that you forgot, okay? It should not be based on memory. And it should be so natural that you cannot forget any of it. Because otherwise it is exactly like that story, which you will watch. Okay, now this goes away. And now look what happens here, guys. So this is going to be x to the power of 4 plus 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 x to the power of 4. How many times do I add it? 5 times. Do you all understand how I obtained that formula, guys? I'm deriving a shortcut, okay? And I not only have to imagine that's correct, it's good if you notice a pattern, but I have to verify that I'm not ever making a mistake. Okay, so now let's do it in general for z to the n minus x to the n. Okay, so z to the power of n minus x to the n is z minus x, z to the power n minus 1 power less, plus all the way until I have no more z. You understand? Z will give its power. It's very easy to remember. One power after another until there is no more z. Good? Here it is, guys. So here is z to the 6 minus x to the 6. You see, z to the 5, z to the 4, 3, 2, 1, 0. Yes? This is a verification that the pattern is correct for an arbitrary n. So I don't have to do long division. Long division becomes longer and longer with bigger powers. So I can do it this way. If S is this summation, then Z times S is just multiply everything by Z. It's this thing. And if I multiply S by X, it's this thing. When I subtract ZS minus XS, what survives, guys? Look at it. They are canceled. They are canceled this way. Look at it. Z to the n plus X to the n minus 1. Look at it. If I subtract, it's z to the n. This is canceled with that. This will be canceled with the next term. This will be canceled with this term. There is only surviving terms are z to the n and x to the n, which is what you see over here. So that's z to the s minus x to the s, that's z minus x times s, which will be z to the n minus x to the n. This is just, again, guys, a verification that if I notice the pattern, I can easily verify that the pattern I noticed is always holding for any powers. I'm easily able to factor not only difference of squares, but difference of cubes, difference of any powers for any integer power. And so now we are going to calculate the derivative of x to the n, where n is a positive integer. Note, where n is a positive integer. Now, the derivative will be drop this power down and subtract 1 from the power. You understand what we're doing, guys? We're developing shortcuts so we don't have to repeat the same process all the time again. So what do we have here? We have the limit of z to the n minus x to the n over z minus x. And when I factor it out, the z minus x, they cross away, and I'm left with z to the n minus 1, that there's a 0x, 1x, all the way to n minus 1x's. Altogether, once I push z towards x, this becomes x to the n, this becomes x to the n. How many totals? A total of n x to the n minus 1s. Do you see that? I'm not moving too fast, right, guys? You understand, you understand why that limit gives you n times x to the n minus 1. I know some of you are thinking, I don't care, I want to memorize it. If you understand it, guys, you end up just easily getting A. If you don't understand it and memorize stuff, your memory will falter. You are not able to think. You are not able to you're not able to find your left from your right. You're lost in the forest. You're not familiar with the territory. You will be lost. You understand? You can decide what you want to do, up to you. But trust me, you see, understanding equals good grade. Not understanding equals bad grade. Unless you manage to cheat and I do not catch you, of course. But then you are also clever. So what does it mean, guys? This means what we just verified is that the derivative of x to the 6, I don't have to bother anymore with that long procedure. It's just 6x to the 5. It means what? If I want to find the derivative of this function, I just take the horizontal coordinate, take it to the power 5, multiply it by 6. The derivative of x to the 101 is 101 x to the 100. Derivative of x to 30 is 30 x to the 29. we have our first shortcut. Clear? Now, we need to, once we have this shortcut, we now are going to try to calculate some derivatives, okay? So for example, what happens if I add two functions? I know how to take the derivative of one function and the derivative of the second function. Let's see what you might say, guys. So before I do anything, all right, suppose that you have x to the power of 5 plus x to the power of 7, and you want to take the derivative of that. What's the result? What do you think is going to be the result? You can do faster, like intuitive, if you have an idea. This function is f, and this function is g. And this is some sort of f plus g. Well, good, good. A lot of you right away reacted. You think, oh, it's probably going to be the derivative of the first function plus the derivative of the second function. Yes, so you think, oh, I know how to take the derivative of this piece, which is 5x to the 4, and that's my f prime, plus the derivative of the second piece, 7x to the 6, and that's g prime. Yes? So you think that the derivative of the sum is the sum of the derivatives. Is it true in general, or is it just true for those particular functions, right? That's how you formulate your theory. Good? All right, let's just see for a moment, guys. Okay, so this thing, right? What do you think would be the derivative if I have 10x squared minus 3x cubed? What do you think the derivative would have been now? So this, you were right. Well, okay, a few people already answered. You're very quick. 1, 2, 3, 4, 5, 6. Come on. We have here 33 students or 32 students. What about the rest of you? I want to see people I want to see everyone participate. Okay, good. So this is, you think 20x minus 9x squared. Yes, 20x minus 9x squared. Beautiful. Now tell me, what do you think is going to be the derivative of x to the 5 divided by x to the 11? What's the derivative? What do you think? Okay, Nicole went through it. Okay. Elazar. Okay. So let's see a few more of you. I want to see what you say. Sophia, interesting, interesting. Now the answer is, right, obviously, correct? Obviously, 5x to the power of 4 divided by 11x to the 10, right? How many of you get it, right? That's so obvious, correct, guys? So very, very obvious. So very obvious because it is absolutely wrong. You see, if you're going to guess stuff and not understand, you will right away be lost in a forest. It's complete nonsense. So you see, some people, of course, ask, why do you not memorize some procedures? I mean, first of all, nobody cares what you memorized, right? It's like you memorize your way to walk like a horse, right? To drag some stones to the quarry. Congratulations, you beast of burden, right? I hope that you are interested in something more. For that, you need to think about it. Okay, guys, we will talk about this derivative. For that, you can take a guess. You can make a hypothesis, but always justify your hypothesis before moving on. If I had ill intentions, and I will always harbor ill intentions, I will, let's say, maybe my goal is to first make you believe and then feed you misinformation because I want America to fail to the glory of Russia, right? If that's my goal, I can easily do that because you just believe you're led by the nose. Well, actually, I don't need to do that. It's, you know, it's happening without my help. Do you understand me? So those are the limit laws or the derivative laws. We are going to prove them. 1, 2, and 3. Let's get started. So we are going to prove 1 by definition. If this is my function, by definition, it's CFZ minus CFX divided by Z minus X. And I simply, what am I searching when I say, I'm assuming here that I know the derivative of F, which I can represent by F prime, you understand? And it's a sort of recognition. When I take the limit in an unfamiliar expression, I want to see the familiar expressions that are the definitions of the derivative of my function F. So beginning with the first, the derivative of a constant times the function is constant Fz minus constant F of X divided by Z minus X. I factor the constant. What do I see here? I see F of Z minus F of X over Z minus X, which I instantly recognize as the definition of the derivative of F. And if it exists, it's going to be constant times the derivative of F. Yes? So what does it mean, guys? This rule allows you to do such calculations. So for example, if I have 5x squared, right? What is that? This is 5 times f, where f is a function I know how to differentiate. So when I want to take the derivative of that, I'm told skip over the 5 and just take the derivative of that function. You understand? Which is what you guessed correctly. So it's 5 times 2x, which is 10x. You understand what that rule just explained? And you understand why that rule is true. We just verified why it's true. Yes? Nobody had any trouble with it. Correct, guys? I'm not sure if you see that. Is it a mystery, guys? But isn't the derivative of a constant 0? Why am I skipping over a constant? Isn't it 0 because its derivative of 5 is 0, correct? Right? I mean, isn't it right? Let's say this is 5x squared. I take the derivative, but the derivative of 5 is 0. So isn't it 0 times 2x, which is 0? No? Anyone is bothered by what I just did or not bothered at all because it's complete nonsense? Or does it bother you? You think it's actually, oh, it's a riddle. I'm not sure what to do here. Is it a riddle? Okay, cool, cool. So before I explain, guys, I mean, I just said something that in my mind, I mean, it's not even a question. But, and I'm not, and therefore, because it's not even a question, I might not have deceived you well enough, right? Is this something that bothers you? Shouldn't I take the derivative of 5 and make it 0? No. Would anybody tell me why is the derivative of 5 standalone equal to 0? if I have f of x equal to 5, why is the derivative 0? Slope is 0, it's a line, right? Now, if I said f of x equal to 5x squared, could the derivative of that be 0? Could it be 0? No, it could not be 0 because the function is not a line to begin with, and definitely not a horizontal line. 5x squared is a parabola, you can see it climbing up. So, right, so there should not be any confusion. Obviously, the derivative of 5x squared is not a derivative of 5 times the derivative of x squared. That's impossible. Because if it were, it would violate that essence. You understand what I mean, guys, right? So my point with such stupid examples is this. I mean, it's a non-confusing thing for a person that understands. You cannot even be led like this. It cannot even occur to you, like, what is this nonsense? Because you completely understand what you're talking about. You memorize nothing, or maybe very tiny things that are obviously very essential, but you know, it's just obvious to you what's happening, right? Derivative slope of a curve is this. So what do you do there? All the rules that I develop, I know how I develop them, I understand how it works. Then I cannot be confused. If I memorized, I mean, I can be told all sorts of nonsense. Do you understand, guys, that this is what we verified? The derivative of a function multiplied by a constant, I can skip the derivative and push it to the function. And the reasons for that are trivial. Because look at it, the derivative of this, of c times f of x, is z going to x. Let's call this function g of x, right? So that's the limit as z goes to x of g of z minus g of x divided by z minus x. What is that? This is limit as z goes to x of c times f of z minus c times f of x divided by z minus x, yes? And so what can I do here, guys? Do you understand what I'm doing? I'm using pattern recognition. If I understand how to take the derivative of f, all I need to do is just factor out the c. So it's c times limit as z goes to x, f of z minus f of x over z minus x, which is c times f prime x. You understand? I don't use any ideas that I haven't verified, that I am not comfortable with. That's another essence that I'm trying to show you, right? So, and if you're very comfortable with those ideas, you can play with them. You can derive things that nobody ever showed you. And you don't need to be a genius for that. I mean, it happens all the time whenever you are doing something interesting. Like if you read a physics book, you will do that all the time. You will play with the idea. You cannot play with the idea if you memorized it. Good? Now, with the addition, guys, it's too bad I cannot bring you to the desk, you know, in front of the desk and do that. Derivative of f of x plus g of x. Why is it the sum of the derivatives? Because look at it, by definition, it's this function. It's one function evaluated at z minus the same function at x divided by z minus x. I can regroup it into f of z minus f of x over z minus x and g of z minus g of x over z minus x. So I recognize this piece to be the derivative of f and this piece to be the derivative of g, which means that we have f prime plus g prime. You're clear, guys? You see, I just verified that I can use the derivative rule for addition and for scalar multiplication. So rule number 1 and rule number 3 allow me to take right now derivatives of functions of this form. I can, for example, say what's the derivative of 2x cubed plus, or 2x cubed minus 5x squared. The derivative of that will be 2 times the derivative of x cubed, which is 3x squared, minus 5 times the derivative of x squared, which is 2x. You see, and that's why the initial guess that you had, the initial 2 guesses worked, because those processes happen like you expect them to happen. With the quotient, they will not happen as you guessed. Good. Here is that property. Property 1, scalar multiple. Do you see that? Combining properties 1 through 3. 3 is the same with subtraction. It's not even necessary to write it as a separate process, because subtraction is minus 1 multiply. It's addition with minus 1 multiplying this thing, right? Elazar, you look like you grew a beard very fast. I guess the class was happening so long. But yes, you became a bearded wise man. Understood, guys? So, right? Property 3 is just this. It's scalar multiplication and addition easily. Yes. So what you understood again, just to be sure. So if I want to take the derivative of f of x minus g of x, that's the same as taking the derivative of f of x plus minus 1 times g of x. And I already know using laws 1 and 2 how to do that. Yes, so property 3 is either by direct definition or somehow else. It's very obvious. Now calculate the derivative of this expression, guys. Very fast. You can use shortcuts. When you see on the exam, if I tell you calculate something like this, you don't have to do it by definition. You can do it any way you like. But if I say use the definition of the derivative and you just give me a shortcut, you get no points for it. Okay, very good. Very good, guys. Here it is. Minus 2x plus 27x squared. Yes, everybody understands this? Very easy, correct? Just take the derivative of 10. Derivative of 10, it's a constant, it's 0. Derivative of minus x squared is minus 2x. Derivative of 7x cubed is 27x squared. Not hard, yes? Oh, so we are almost, our time together is almost done, guys. Allow me two more things to say. Two more things. First, guys, tell me what's the derivative of 2 to the power of x. Okay, Kevin says 2. 2x, well, whatever. So before we get there, guys, let me actually teach you something I learned very recently that will be maybe fun for you, right? That was from What, When, Where, and I'm not gonna play it, I'm just gonna write it, okay? The question was this. Are you ready? In what school, in what lesson in school do you learn the following sentence? May I have a large container of coffee? In what lesson do you learn this sentence? Moshe, we are never done. So what do you think? In what school class do we use this, if I spelled coffee correctly, of course? Home economics. English class, you're saying. Language class, yes? I'm not gonna torture you long. If you play What, When, Where, guys, it's a What, When, Where question, right? If it's a What, When, Where question, it's never stupid like this, right? Obviously, it's not in an English class. You want to know where you use it? Exactly. It's a math class. Do you know why? Do you know what it is? It is, look at it, May, it's 3 letters. So it's 3, I is 1, have is 4, 1, 5, 9, 2, 6, I believe, if I spelled correctly. This is the expansion of pi. You're welcome. Remember it, may I have a large container of coffee, gives you a bunch of digits of pi just for fun. When you're lost without a calculator, you know. Good? All right, guys, so I'm going to, oh, some people join. I'm going to stop the recording. We're going to continue with 2 to the x on Thursday, right? And if you want, we can play a little bit more what, when, where, very nice questions, and other things, up to you. We can solve a bunch of questions here, derivatives, practice, and if not, goodbye, auf Wiedersehen, see you later.
Have a good night, Professor.
Good night.
My kids thoroughly enjoyed your lecture.
Yes, well, I guess I can be used as a soporific. I guess they fell asleep. Right?
No,
They
they're
were
up.
traumatized, they lost their ability to speak. One or the other.
They're up, shockingly.
Okay,
All right, have a good night, Professor.
good night.